Okay, in this video we're going to see how we can compute limits algebraically, and to do that we're going to need some rules and then some just basic algebraic manipulation that we've learned in an algebra class probably before. So let's first go through some of these limit rules. So we have to set this up. We're going to say we've got two limits already. Let's say we've got that the limit as x goes to c, some c value of f of x is equal to L, and let's say we have another limit of a different function, but we're still going to the same value. So our inputs are still approaching the same thing. And I've got a different function though, g of x, and those outputs, they approach m, and k is real. So I've got another number k, which is a real number. So we want c, l, m, and k to be real numbers. And I've got two different functions, f and g, and we have this relationship between those functions, the input c, and the limits at l and m. Okay, then we've got a few different rules, right? If I take the limit as x goes to c of f of x plus g of x together, well, we know that as the inputs get close to c and f, this stuff gets close to L, and this stuff gets close to m. So when you add them together, they get close to L plus m. So that's not too far-fetched to think that that would happen. If f gets close to L and g gets close to m, then f plus g should get close to L plus m. Similarly, if you do subtraction, limit as we get to the same point, f of x minus g of x, this is going to be L minus m, and then limit x goes to c of this k value times f of x. So if I make all the outputs k times as big, the limit should be k times as big. Right. So those are our three sort of linear things for the limits. The product rule, so if I take the limit as x goes to c of f of x times g of x, well, if these guys are getting close to L and these guys are getting close to m, then these together as a product should be getting close to L times m. If m is not equal to 0, I should be able to divide by it, and that is the case. The limit as x gets close to c of f of x divided by g of x, this should get close to L divided by m. With that repeated multiplication, we can do powers. So if n, let's call it alpha, so it's any real number. If alpha is a real number, then the limit as x gets close to c of f of x to the alpha, right, should be equal to L to the alpha, right? So if alpha is a positive integer, like a square, or a 2 for squaring, 3 for cubing, and so on, and then the limit is squared, the limit's cubed if the function was squared or cubed. If it's a fraction and you want to take a root, the square root of f, then you should take the square root of the limit, that kind of thing. And then lastly, and this one's kind of nice and important later on in calculus. We won't see it too much in this section, but it's really a powerful tool. If, say, h of x is a continuous function, how composition works with this limit is we've got the limit of h of f of x as x goes to c. So we know what f of x does as x goes to c. It goes to L. Since h is continuous, this limit is going to go to h of L. Okay. And that's pretty powerful as a tool later on. Okay, so let's see some examples of these things. Let's look at this one. Let's look at the limit as x goes to 2 of, let's say I've got the function x cubed plus 2x squared plus x minus 7. Okay, if I look through my rules here, I've got addition in this function, I've got subtraction, I've got constant multiple stuff, right? I've got power stuff. Okay. So one of the easiest things to do is we can take the limit of what x is as x goes to 2. But we're going to break this up into 4 bits, and this is going to be equal to the limit as x goes to 2 of x cubed plus the limit as x goes to 2 of 2x squared plus limit as x goes to 2 of x plus the limit as x goes to 2 of negative 7. Okay, and each of these is really easy to compute. So the power rule says since x gets close to 2, this should get close to 2 cubed. So this is going to be 8 plus, as x gets close to 2, this should get close to 2 times 2 squared, which is also 8. And then as x gets close to 2, x gets close to 2. And as x gets close to 2, negative 7 always stays negative 7, so that output always stays at negative 7. I end up with 11 here. So the limit of that would be 11. We've kind of broken things down extensively to solve this polynomial deal. But as long as things are continuous, right, this polynomial was a continuous function, and I can think of f of x as just being x. So if f of x is just the function x, whatever this is, I can plug it in as long as h is continuous. Polynomials are continuous, I can just plug 2 in and have that work out for me. Let's see one more example. Let's do the limit as x goes to, let's go negative 2. And we're going to take the function being the square root of 4x squared plus 3. Okay, the square root function is a continuous function as long as you're not plugging in negative values, but this thing is never negative because it's a squared, which is a positive thing, plus 3, which is a positive thing. So we should be able to just plug in negative 2 into this, and we will get the square root of 4 times negative 2 squared plus 3, which is the square root of 19. Okay. So our limit rules are kind of nice. Sometimes we can't use those limit rules because we don't have continuous functions. So let's look at some examples where we don't have maybe a continuous function. Let's look at this one. Let's take the limit as x goes to 0 of, I've got the square root of x squared plus 100 minus 10 divided by x squared. Okay, this isn't a continuous function, especially not at this point that we're trying to evaluate the limit, because I've got this x squared in the denominator, and if I plug 0 in, I get division by 0. Okay. In fact, the numerator is also 0, right? So if we plug this in and we ended up with 0 over 0, that means that we can probably do some algebra to work with this and simplify things a bit. So let's try and do some algebra to simplify this a little bit. So this is still the limit. I have to carry that limit through because I haven't actually taken the limit yet, so we always, until we actually take the limit, we write down that we still need to take the limit. So we still need to take the limit as x approaches 0, square root x squared plus 100 minus 10 over x squared. And I'm going to rationalize the numerator. And if I rationalize the numerator, maybe some things will cancel. So to rationalize the numerator, I multiply the top and the bottom by that conjugate. So the conjugate of that numerator is x squared plus 100. I had a minus here, so I'll have a plus 10. And I don't want to actually change anything because I wrote down an equality. So if I don't want to change anything, I have to divide by the same thing I just multiplied by. So x squared plus 100 under the square root plus 10, not under the square root. Okay. And we'll do the algebra here. This is the limit as x goes to 0. We haven't taken that limit yet. We've just kind of rewritten things and need to do some algebra yet. Because of this conjugate, this and this are conjugates of each other, I get a difference of squares. Right? I've got this a minus b, a plus b stuff, and we know that a minus b times a plus b is a squared minus b squared. So I square the first thing, and I get x squared plus 100, right? Squaring something that has a square root over it just gets rid of the square root. And then I'm going to subtract off the second thing squared, so I have to subtract off 10 squared, which is 100. And then the denominator, I've got an x squared, I've got a square root of x squared plus 100 plus 10 down there from this side. Okay, so I've simplified things a little bit. We can simplify things a little bit more. I still haven't taken a limit, so I keep writing that limit goes to 0 down until I actually take the limit. Okay, I've got x squared plus 100 minus 100. Okay, so those 100s cancel. I end up with an x squared. I've got that divided by an x squared. Oh, that's going to be nice because those are going to cancel, right? And then I've still got the square root of x squared plus 100 plus 10. Those will still be down there. But I get to cancel those, and this is going to be the limit as x goes to 0. I haven't done that yet. I haven't plugged in x equals 0 anywhere or anything. I've got 1 divided by square root of x squared plus 100 plus 10. Okay. Now if I plug in x equals 0 into this, I don't have division by 0 again. I don't have anything breaking, so we can actually evaluate this by putting in the 0 for the x squared. I get 1 over the square root of 100 plus 10, which is 1 over 10 plus 10, or 20. 1 over 20. So we had a 0 over 0, and we ended up being able to do some algebraic manipulation to compute the limit, which is going to be 1 over 20 in this case. Okay, so let's see if we can do some more of this type of thing. Let's look at another one where I maybe get a 0 over 0. So let's look at the limit as x goes to 1. And we're going to have t squared plus t minus 2 on the top. We're going to have t squared minus 1 on the bottom. Okay, if I plug in 1, I get 1 plus 1 is 2, minus 2 is 0 on top. And if I plug in 1 on the bottom, I get 1 minus 1 is 0. So this looks like a 0 over 0 again, which is a good hint that we can do some algebraic manipulation with this. So let's see if we can simplify things, and the first way we're going to do that is we're going to factor stuff out. I have to write this limit out again still. The numerator, it factors as x minus 1 times x plus 2. The denominator factors as x minus 1 times x plus 1. Okay, and it looks like some stuff cancels. This x minus 1 and that x minus 1, they get to cancel. Okay, now if I plug in 1, nothing goes wrong. I don't have division by 0 or anything, so I can plug in the 1 here, and I end up with 3 on the top and 2 on the bottom. So this limit evaluates to be 3 halves. Okay, let's do one more of these, and then we'll talk about the squeeze theorem really quick, or the sandwich theorem real quick. Okay, so let's look at the limit as h goes to 0 of 3 divided by the square root of 3h plus 1 plus 1. Well, that's not that silly. We can just plug that one in, can't we? I thought this was going to be a tougher one. We don't get 0 over 0. If I plug in h equals 0 into this, I end up with 3 over the square root of 1 plus 1 is 3 halves again. So let's see if we can find one that does look like 0 over 0. And yeah, there we go. Do some more algebraic manipulation. Okay, here's one from the book that looks like 0 over 0. I'm going to take the limit as x goes to negative 3. We're going to take 2. We're going to have minus the square root of x squared minus 5 divided by x plus 3. Okay, if I plug negative 3 in, on the top, under the square root, I get a 9 minus 5, which is the square root of 4, which is 2, so you get 2 minus 2 on top, so this goes to 0 on top, and 3 plus negative 3 is a 0 on bottom. This is going to look like 0 over 0 again. So that means we can probably do some algebraic manipulation. And how do I want to do that? Well, I'm going to multiply. I'm going to clear out that numerator. We're going to multiply that numerator by 2 plus the square root of x squared minus 5 divided by 2 plus the square root of x squared minus 5. We'll multiply top and bottom by the same thing, so nothing changes. We can write down equality. And the top is going to be, we haven't taken a limit yet, so we write that down still, minus 3. And then I have a 4, and I've got a minus an x squared minus 5, right? And then on the bottom, I have an x plus 3, and I have a 2 plus square root of x squared minus 5. Okay. So we look at this. The numerator, it looks like a 9 minus x squared. The denominator, I've got this x plus 3. I've got a 2 plus the square root of x squared minus 5 down there. Okay. I still have 0 over 0, but we can actually simplify things a little bit now. The numerator will factor, right? The numerator factors as 3 plus x times 3 minus x. I've got this x plus 3. I've got the square root, no, not the square root yet. I've got a 2 plus the square root of x squared minus 5. I have an x plus 3 and I have a 3 plus x. Those are the same thing. Those can cancel. Now, I plug in a negative 3. A 3 minus a negative 3 is a 6. So 3 minus negative 3 is 6. And then on the denominator, I have a 2 plus the square root of negative 3 squared is 9 minus 5. So this is 6 over 2 plus 2 is 6 over 4 is 3 halves. So that one we had to do a little bit more algebraic manipulation to compute that right there. Okay, the sandwich theorem, the squeeze theorem. Let's just draw a picture and see how this works. So the sandwich theorem says if you are trying to take a limit and you squeeze two numbers together, then the thing in the middle has to be between the top and the bottom, basically. If two functions are always on top and bottom of another function, and those two functions go to the same spot, the middle function has to go to the same spot. So let's say I've got this picture. We're computing a limit here at c. I've got function 1 that does something like this. I've got function 2 that does something like this. and I've got function 3 that always lives in between them. Right. So let's say I have f of x here, this is g of x, and this is h of x. So the statement is, if f of x is bigger than or equal to h of x is bigger than or equal to g of x for all x, and the limit of f of x as x gets close to c equals the limit of g of x as x gets close to c. Let's call that L. So this value is going to be at c comma L. Then, these are not equal to c. Then the limit of h of x, the one that's in the middle as x gets close to c, also equals L. Right. So if this yellow function is always between the red function and the gray function, then the limit of that yellow function will be between the red function and the gray function. So if the red function and the gray function come together at that limit, the yellow function has to be there too. Okay. And that's all the sandwich theorem says. We'll leave that at that. Alright, that's all of 2.2. I'll see you for 2.3 next time.